Okay, everybody, we're going to start talking about enols and enolates, which ultimately leads to alpha carbon chemistry. As I said before, we've been talking about essentially different carbonyl groups. And so if we kind of rewind a little bit where we are at this point, we started with talking about ketones and aldehydes and all of the different nucleophiles that react at that carbon, at the carbonyl carbon. Then we talked about what happens if we add an OH to that carbonyl carbon. In other words, make it a carboxylic acid. And then we went, so that led us down the carboxylic acid and carboxylic acid derivative rabbit hole. And so there's a lot of things that were going on with that. But eventually, at the end of the day, it was essentially some type of carbonyl chemistry. Now we're going to continue on with our discussion of carbonyl chemistry. And this time we're going to move one carbon over from the carbonyl carbon. And we're going to talk about the chemistry that happens there. And this is called alpha carbon chemistry, and I'll explain why it's called alpha carbon in just a second. But that's where we're heading. So from going up from this point forward, the videos should be a little shorter because I'm going to make them try to make them as bite-sized as possible in order to be a little bit more digestible and scaffold up the material in this particular section. So let's go ahead and get into it then, and let me start this out. All right, so let's take a look at what I mean by alpha carbons. If I look at a standard carbonyl group, then the carbons that are not the carbonyl group get Greek letter designations. Let me make my gamma a little bit better. Actually, and so what we're talking about when we say alpha carbon is we talk about this carbon here. This is the alpha carbon. Now, this is different. This is a staunch difference between alkyl halides, because typically when we talk about alkyl halides, we also use this Greek nomenclature, but this Greek labeling, but we do give the carbon attached to the halide a letter. In this case, we don't, right? This carbon does not get a letter. And so this is what we're going to investigate: the chemistry of alpha carbons. What we're going to do is we're going to think about different ways that we can do chemistry at that carbon. If I recall from earlier in the chapter associated with alkynes, that a doubly bound carbon double bond that has an oxygen OH group attached to it is called an enol. And we discussed at that particular moment that enols are not favored to form in most cases. And you can tautomerize an enol to a ketone or an aldehyde. And that's really what the results of some reactions like this are. When we think about taking an alkyne and hydrating it, we can think about it in terms of a Markovnikov OH addition to form an enol, but we know that that enol will immediately tautomerize under the acidic conditions to form a ketone. And we talked about the mechanism of that reaction and the mechanism of that formation. And we're going to review that here in just a second. So if I have a catalytic amount of base or a catalytic amount of acid, then I can take a ketone and form an enol. But the alternative is that I can react it with a very strong base. And if I react it with a very strong base, then I get a negatively charged species here that has this double bond. And this is called an enol-ate. And no matter what we're going to do at this point, whether we're talking about enols or enolates, we're going to replace a hydrogen at that alpha position with some other group. And that's what's the chemistry that we're going to discuss in this chapter. Okay. So let's take a look at some of the situations under which enols and enolates exist. Remember, it really is an equilibrium situation. And so under most conditions, the ketone is favored. Under most conditions, the ketone is favored. All right, and so let's give an example. A good example of where the ketone is, the predominant product would be cyclohexanone. Its enol variant is cyclohexenol, and this exists, far less than 1%, and this exists far greater than 99%. Okay. So really under these conditions, the enol is not anywhere, is not favored at all, and the ketone is the most favored species. Now we can start to consider situations where the enol becomes increasingly more significant. Let's imagine a situation where you have a ketone like this next to a ketone like that. Now, if we were going to form an enol in this case, we've got a couple of factors that would be stabilizing the enol. One factor is that the pi system is conjugated. And the other factor would be an intramolecular hydrogen bond. So we have an intramolecular hydrogen bond here, and we've got a conjugated pi system here, and that makes a little bit more stability. In fact, in this particular case, we're saying this version is actually favored to exist, but not quite as lopsided as the cyclohexanone example. And we can continue to go further in this example of, well, where would the enol be favored? And we can give you a clear example of what would obviously be the favoring an enol if we think about phenone. I'm sorry, not phenone, phenol. If we take a look at the corresponding ketone, there's a big deal here, right? This is, in this case, this is much greater than 99%, and this one is much less than 1%. And it's obvious, I think, for everybody at this point in the semester, or at least it should be, that in this case we have aromaticity. In this case, that is broken. And so that's why in this particular case, the enol is the dominant product. So we thought about different situations where the ketone, most cases, this is how it is. The ketone is the dominant product. A situation that does favor the enol, but is not necessarily as lopsided. But then here's the situation where it is lopsided in favor of the enol. Okay, so let's take a look. Go back a little bit into our tautomerization land, back into organic chemistry 1, where we talked about the tautomerization of a ketone and an enol. Now, in general chemistry 1, we talked about it in terms of tautomerizing the enol into a ketone. In this case, I'm going to show you the mechanism in reverse as we take a look at tautomerizing a ketone into an enol. Now, I think we're going to have some review of the chemistry that we have recently discussed in seeing that, well, under acidic conditions, I can't form any negative ions. And so when I'm thinking about what it is that's actually coming in to do some of this chemistry, I'm going to see that one of the only options I really have is to protonate the oxygen. So that's going to form a protonated ketone with a positive charge. And I can show that there's a resonance structure here where there's quite a bit of positive charge that's on the oxygen, or excuse me, that's on the carbon. Right, then water can come along. Notice that there is a hydrogen here. And this is where I get my this is how I form the enol. Now, don't get confused between tautomers and resonance structures. Tautomers, excuse me, refer to constitutional isomers that are separated by the movement of a single proton. Resonance structures, again, are not constitutional isomers. They involve only the movements of electrons. All right, that's acid catalyzed. Let's take a look at the same situation, but with base catalysis. We can ultimately get the same resulting product with base catalysis. But as I said before, we have to think about the conditions of the reaction, and the conditions of this reaction dictate that I can't form anything that's intermediately positively charged. I can only form things that have intermediate negative charge, because that's the conditions of the reaction. And so I'll still end up with a resonance structure that has some resonance stability of the negative charge. And I form this intermediate. We're going to talk more about that intermediate in a second. Let me show the formation of the enol at the end of the day. Here's an enol, but this guy, this negatively charged species here, is the enolate. And we're going to spend a lot of time talking about enolates as well. As a matter of fact, I think that's the very next thing that we're going to do. Right? When we talk about the chemistry of, or when we talk about alpha carbon chemistry, there's a couple of ways that we can show it. Well, first of all, if I'm looking at an enolate, let's go back and take a look at this enolate. I see that there's some possibilities here. In this case, in this resonance structure, it's pretty clear that there's a nucleophilic carbon. It's pretty clear that there's a nucleophilic carbon. When I show its resonance structure, it seems like also the oxygen is nucleophilic. And this, in fact, is the case. So that means that I could have chemistry involved with the carbon acting as a nucleophile, C attack, or I could have chemistry with the oxygen acting as a nucleophile, O attack. Now, in this particular section, we're going to really be talking about carbon attack. And so that gives us two different ways to think about how we're going to show carbon attack from a mechanistic standpoint. I could start with the enolate. And given an electrophile, I can show the carbon attack this way. Or I can show the negative charge on the carbon and show the carbon attack this way. The results of both versions end up with giving me the same chemistry, but for simplicity's sake, most of the time we're going to show the mechanisms with this version rather than with this version. So I want to point this out because it's specifically leads to confusion when we see these things mixed up. It's not that either one of them is wrong or one is more right than the other. It's just that this one has only one arrow. This one has two arrows. And again, you know, chemists are lazy. And so whenever we can avoid an arrow drawing step, then we tend to take that avoidance. All right, so let's take a look. I want to talk about how are we going to form enolates. Enols definitely do some chemistry, but enolates are going to be the things that we're going to most often form, and we'll talk about why that is a little bit further down the line. So at this point, you're going to have to take it on my word that enolates are going to be the interesting species that we want to consider. And so we have to first consider, how do we form enolates? If I take a look at some common alpha protons, what I'm going to see is that their pKa's are not particularly low. The pKa values are, in most cases, and even in this last case, quite a bit larger than alcohols. Only acetaldehyde, only this last one, is even close to an alcohol, and it's still nearly 10 times more 10 times more, 10 times less acidic than an alcohol. And so that's going to have some important consideration when it comes to different reagents that we can use as the base to deprotonate this and form an enolate. Here's the reaction that I'm talking about. And if you recall from the first section of organic chemistry, where we talked about the relative strengths of acids and bases, we see that in this situation, the reaction really does favor the ketone with only a small bit of the enolate. Remember, an acid-base equilibrium will favor the side of the reaction that has the weaker acid, which is there. And so this is true even if we're talking about a very specific aldehyde, acid aldehyde, and its proton. Even under these situations, the equilibrium still favors quite a bit the ketone itself, because the pKa here is still 16.7, so it's still, as I said, almost 10 times larger or less acidic. So in order to form enolates in any large quantity, we need to use really strong bases. And so there's going to be two common options. One common option will be to take advantage of Le Chatelier's principle and remove one of the products that's formed. If I use hydride, to remove the proton, then I form the enolate, and I form hydrogen gas. And of course, hydrogen gas will escape the system, and as it escapes the system, it's going to continue to move the reaction in the direction of products. So this is irreversible in that sense. So this would be irreversible enolate formation. Another way would be to use a common strong base based on an amine group. And the way what we would do is we would take diisopropylamine. There's diisopropylamine, and we react it with butyl lithium. And butyl lithium is something that doesn't get a lot of love from Klein, but it's a pretty common and very, very strong base. It's highly reactive. So what we can do is we can take butyl lithium and we can form this salt. And this is called lithium diisopropyl amide, or LDA for short. Now, the other product of this reaction is butane. And we can go back to our acid-base chemistry and think about pKa's. pKa's of amines are in the neighborhood of 36. pKa here is in the neighborhood of 50. So we see that the butane is a much weaker acid. And so we can use butyllithium to form LDA, and LDA will be a really strong base that we can then use for deprotonating alpha carbons. We can't use butyllithium directly because we would worry about side products, and that carbon would be very nucleophilic, and it would attack the carbon of the carbonyl group. And so it would lead to a lot of different, let me go ahead and draw this out. It leads to side products that we're not interested in. So lithium diisopropyl amide. That would bring the enolate. And I'd also have lithium or I'd have diisopropyl amine. We already talked about the pKa here around 36, and we did already talk about the pKa here. Even in the largest case, we're talking on the order of 19. And so the equilibrium in this case favors the formation of the enolate. So there's two ways to irreversibly form enolates. We can take a look at an enolate formation through removing one of the products like H2 gas, or more commonly, we can use LDA to irreversibly form enolates. Now, there is another situation to think about when it comes to enolate formation. There are cases when I have ketones like this, and I want to consider these hydrogens. Take a look at these hydrogens. The pKa here is actually around 9. And if we think about why that might be, we see that there is resonance stability. But not only is there resonance stability in this direction, I can also show resonance stability in the other direction. And so that leads to a much more acidic proton. Let me get rid of those arrows. And so if I were to go back and take a look at using ethoxide as a base in this case to do the proton transfer, I end up with ethanol as the product. And again, the pKa here is about 16, 15.9. And ethanol is a much weaker acid than the diketone. And so in this case, under these circumstances, I can irreversibly form enolates with using sodium hydroxide. Okay? Or excuse me, sodium hydroxide or sodium ethoxide. And so let's sort of review what's going on with the chemistry here. If I take an enol or a ketone and I react it with some RO base, then I am going to get some of the enolate, but remember the ketone will also be around, so it's not going to be irreversibly formed. If I use LDA or sodium hydride, then I will irreversibly form the enolate. And that's going to have some consequences on the chemistry. Now, one last little thing to remember is that if I end up with a ketone like this, then I can use that weaker base to irreversibly form this enolate. And LDA, sodium hydride, is not needed in this case. Okay, I'm going to leave it there. We're going to move on to actual reactions that involve enols and enolates. And we'll start off by adding some halogens at that alpha position and take a look at the reactions that involve that. Of course, we're going to learn some mechanisms involved with those reactions as well. And so we're going to have to keep in tune. See you later, guys.